Okay. Hello, everybody. I don't know. Okay, so just a recap from last Friday, just to bring you back to what we were talking about, finish this lecture hopefully, and start a new topic today. Okay, so what is a sampling plan? Do you remember when we say sampling plan? What are we planning? Yeah, it's been a long weekend, hasn't it? Okay. Fedora.
How are you going to I guess take samples of things from like lots? So like, are you going to like pick things randomly, or are you going to find like see something that all the line, or like open it by lots?
That's very good. That's the one of the most, or a couple of the most essential things in sample plan. What are we sampling? How many samples are we going to take out? Randomly, not randomly, using probability sampling, which we'll talk about today. Another important aspect of sampling plan is how we prepare our samples as well. How do we store them so that we don't alter their characteristics? And if there is a transportation, how do we transport them? Like in sealed containers, flushed with nitrogen, on ice. So all of that, all of this goes into sampling plan. Okay. Now, why is sampling plan important? Why is it important that we plan how we sample, how many samples, how we prepare the sample? Why is this essential when we're analyzing food products or ingredients? Why is it important that we have a sound and reliable sampling plan? So that we can
have like an accurate prediction of like what's sampling, so you want to get right.
I love the words accurate prediction or depiction. Yes, even better. So yes, representative sample. So we are taking samples that are representative of the whole lot so that we can make an accurate and precise decision based on the data that we obtain from these samples, so that we can trust the observation. So if we observe XYZ, we can trust that the whole lot can be accepted or the whole lot can be rejected, or so we can make a kind of a sound decision. Okay, what is the difference between attribute and variable sampling? That's a very common question I ask in quizzes or exams. So I would give you a scenario and then I tell you, do you do attribute sampling or do you do variable sampling? Okay, Ash?
Attribute sampling would be testing for the like existence or non-existence of a certain thing. There's variable sampling, it's like testing for the levels of it. So say you have you wanted to test if like chocolate bar had salmonella or not, that would be attribute sampling. But if you wanted to check like the level of salmonella in the chicken, that would be variable sampling.
So you're 90% correct. So basically attribute sampling, if I want to think about it, I would think about it about something, I'm measuring the presence of something that is randomly distributed in my sample. So that can be on the surface of my sample, can be on the side of my sample, can be in one container, it might not be in another container. So when I'm not having a randomly distributed attribute, I would go for attribute sampling where I take a lot of samples out. So I want to make sure that I screen enough samples so that I can say this lot is acceptable and safe, free of salmonella. It doesn't have Clostridium, it doesn't have aflatoxin. So I can be sure of something that would potentially be present randomly across my different samples within a lot. Attribute, that's attribute. Variable sampling is, we are measuring, you're right, Ash, we're measuring the quantity of something that is uniformly distributed within our sample. So moisture content, ash content, protein content, sugar content. We expect that these components are dispersed equally among the different cans or within a sample. Across my entire flour bag, you would have consistent moisture content or ash or whatever. So, and it is on a continuous scale because it's quantifiable on a continuous scale. And normally you don't need that many samples because they are uniformly what do you call it? The word distributed within your sample, so you don't have to take multiple replications. You take like 3 replications, potentially 6 replications, but not necessarily 40 different cans of whatever 1,000 cans, where you want to make sure you don't have an outbreak or a salmonella or clostridium or any aflatoxin, for example. What is a composite sample? Do you remember for nutrition labeling? Yes, Ian?
That you take several samples from different parts of the lot and combine all those samples and then do that.
Absolutely. So that leads to the next question, that the FDA requires for nutrition labeling 12 different samples that you take within the lot randomly, and then you combine them, you form a composite sample, and from that, for nutrition labeling, you have to take 6 subsamples. So that answers these 2 for later parts of this lecture. And this is where I stopped last time. And here we call it acceptance sampling, where you take a sample, and then based on this particular set of sample, you either accept or you reject the lot. So basically, single sampling is often used when you have a uniformly distributed variable. And then you take few samples and then you determine the amount, the composition of a certain component, fat content, for example, moisture content, and it is above or below what you need, then you reject your lot, and then either you reformulate, you readjust your processing, you go back to the process line, you fix some. Double sampling for accept or reject. In this case, for example, I showed you this earlier. You take a number of samples, set number of samples randomly, and then you get the measure. If the measure is above a certain defect level or action defect level, if it's less than or equal a certain action level, you say accept the lot. If it's greater, then you need to do more testing. So you bring more samples and then you take another set of measurements, and then if the value is still greater than a specific number where you have to reject, you reject the lot. If it is within accept or reject, you continue sampling. That's where you continue sampling. If it is above a critical number, you reject. If it is between the critical and acceptable, you continue sampling. And then based on the measurement you get, either you accept or you reject. So that's an example of double sampling. You take out a sample from the population, and based on the results, you either accept, reject, or go for a second set of sampling. Okay, multiple sampling is a little bit more complex. So in this case, you take a certain number of items, let's say 5 samples, and then you determine how many of these samples are defective. If it is, let's say, it lies here, let's say you take 5 and 3 are defective out of 5, you reject. If it is, let's say, 2 out of 5 are defective, then you continue sampling. If it's 0 or 1 out of 5 are defective, then you accept and you stop sampling. So that is, that's what multiple sampling is. It depends on the number of defects and the number of items and where your value lies. Here, you continue sampling. Up here, you reject. Down here, you accept. Okay, so when monitoring food safety by measurement of mycotoxins. Okay, so mycotoxins, they're produced from certain fungal species, and they can potentially be present randomly. So not on a uniform, not in a uniform manner. So what do? Many randomly selected samples are required. A single sampling plan is required. Sampling error is many times greater than the analytical error. So that means this last one, the error associated with making a sampling mistake is greater in consequence than the error made during your analysis, your actual analysis. So what do you think is the correct answer? Carol?
I think it's C, but I also think they can be given A or B with C.
Okay, so C is definitely correct. We'll go there.
It's A and C.
It's A and C, Ruthresh and Isaac, you agree? You agree? I see nods. All right, yes. Priyanka also agrees. Okay. So yes, it's A and C, definitely. Because if you make mistake in how you select your sample for analysis, if you don't take enough number of replications, then you're probably going to make a wrong judgment. You might get 3 samples from 3 different locations, and they will all be free of aflatoxin or mycotoxin. But then there might have been a sample somewhere that you didn't select that could have a mycotoxin, and that could be a high risk on your consumer. So the more samples you select and randomly using a probability way of selecting samples, which we'll talk about, then you will reduce the potential of making a wrong decision. So the sampling error is much greater or of a greater consequence than analytical error. Usually, you are a trained analyst, your instruments are well calibrated, you shouldn't be making a lot of error when you are doing the measurements. But if you do a sampling error in this case, it's more consequential. Consumer risk. So you always want to minimize consumer risk. But at the same time, you don't want to reject a good lot because that will make you lose money. But safety comes first. So the probability of accepting a poor quality population should always be less than 5%. So you want to reduce the risk of accepting poor quality so that you protect the consumer. But also there is a vendor risk, because if you reject a good lot, you're losing money. So basically, but this risk would have greater than 5%. So it would be 5 to 10%. So you probability of rejecting a good quality population should be in 5 to 10%. Not 20, not 30, because that would be potentially a loss to the vendor, economic loss to the vendor. So to summarize, your sampling plan should be simple and flexible. It should be, meaning simple and flexible, you do not want to oversample, but at the same time, you want to be able to say it's a safe plan and I'm covering both the consumer risk and vendor risk. And then also I want to ensure the reliability of the results by making sure I'm storing the sample accurately, I'm preparing them so that I have accurate results, and I'm transporting them under proper conditions so that I don't change anything that might impact the results. All right, so here's an example of sampling. Let's say you are producing 100 bags of flour a day. So that's your lot. You're not going to measure all 100 bags. So you want to pick randomly the square root of the number of sacks in a lot. Let's say you have 100 for simplicity. You randomly select 10 bags. And from each bag, you want to pull out the sample. And the AOAC method dictates that you pull 2 samples of each bag at opposite corners. So you draw a sample from one corner, diagonal to the center, and then you draw a sample from the other opposite corner. You make it a composite sample, and you store it in clean, dry, well-sealed container for analysis. That is the official method of sampling for bags of flour. So if your sample is homogeneous, that's why in a bag of flour, the sample is homogeneous, you can pick from 2 locations. So it's homogeneous, you don't need to do much about it. If a heterogeneous, and usually like it is different packages, different containers, so you cannot necessarily just take one bag from here or one package from here or one can from here. You want to make sure that you do some random and selective or statistical way of picking out these cans. So you draw it from multiple locations and you really try to draw it statistically, and we're going to talk about that in a minute. Sometimes you can do mechanical sampling as well as manual sampling. Manual sampling where a person goes in and pull out a sample, that's prone to human error. Mechanical sampling is less biased, obviously, and this is usually done online during the processing. So if you have milk going through the process, you can have a mechanical, way of pulling out a certain volume, or if it is a solid, you have a core sampler that goes in and pull out a sample from a solid sample. It could be timed during the process, like every 2 hours, a sample is taken out mechanically, less prone to bias. So you can program sampling based on time. And here where I'm going to talk about a little bit about non-probability sampling and probability sampling. Non-probability, you cannot apply statistics. So here what you can do is just take out a sample based on the experience of the person. So here is a truckload of grain. So the person is coming out of experience, just goes around and pick out sample. So judgment sampling based on the experience of the person that's been dealing with grains or seeds or what have you. Restricted sampling, that means if you have a big silo of grains, you can't reach to the bottom, so you have to take a sample from the top. You can't do much about it, you cannot homogenize, you just have wherever you can reach, you can take a sample. That's restricted sampling, there's nothing you can do about that. Probability sampling, that's where you can do this random sampling. And usually when we say random sampling, we involve numbers. So do you remember random table of numbers or random number tables? So basically you select numbers randomly and you have your cans or boxes or bags all given random numbers, and then you randomly select 12 if it is for nutrition labeling. You select 12 numbers and you go get the bags associated with these numbers. So these are randomly selected, no bias, and therefore you can trust the results. Systematic sampling, that is based on what we explained as mechanical sampling. Every 2 hours or 3 hours in the process, a sample is drawn mechanically out. Stratified sampling, let's say, there's an example in your chapter. Let's say a company has different plants that produce tomato soup. All of them are producing the same tomato soup, the same canning procedure. So they would potentially go to every plant and select randomly using random sample or random sampling samples from each of the plants, and they can mix and match. They can make composite samples from these different plants and do the testing. The cluster sampling is similar to the stratified, but more streamlined. You have the same set of number of plants producing the tomato soup. So you number, you give the different plants numbers, and then you randomly select numbers. So let's say you have 10 plants, you select 3 numbers, and you say, okay, I'm gonna go to the plant in California, the one in New York, and the one in Georgia. And I'm gonna take samples from there, rather than sampling each plant. And you can do that, pick different plants each time. And the composite sampling, we talked about that. You take, and this is mostly commonly used in nutrition labeling. You take different samples, you prepare one composite sample, and from there you do subsampling to do your analysis. So, based on what we talked about, the following are potential problems associated with sampling that may result in reduced reliability. Okay. Non-statistical viable convenience, poor storage condition, mislabeling of samples. Ruth Rich? It is all of the above. So when you don't have statistics, you don't have randomly selected samples, it's just where you can reach for convenience, and you don't apply statistics, then there's potentially a problem with sampling. Poor storage conditions, so high humidity, high temperature, not sealed containers, then you're going to change the composition of your sample, you're going to impact the results. Mislabeling of samples, of course, so you just labeled corn, soybeans, and soybeans, wheat, of course, you're not going to get good results. Particle size is really important when you're doing measurement. I give an example, every year I give some example, it just kind of like surprised me one day. The capstone group, you're going to be in a capstone group, and you're potentially going to need to do some analysis. So I walked into the lab one time, and the capstone group wanted to determine fat content in their chips product that they were producing. And they were using a Modiner flask, which you will be using in the lab. But basically, they have to put 2 grams of sample in this flask, and they have to put diethyl ether and petroleum ether, shake, and then separate the aqueous from the organic, where you have the fat. So I walk in, and they're just hard at work, and I look in and I see pieces of potato chips inside of the flask. And then, what are you doing? They're extracting fat. You can't extract fat from large particles. The fat won't come out. You need to reduce the particle size. So I had them repeat. I'm not sure if they liked me at the time, but well, they were gonna really have serious underestimation of fat content. So basically, you need to enhance the surface, the surface size. So by enhancing the surface and the accessibility of the solvent to your particle, to your component, you have to reduce the particle size and enhance the surface area, basically. So what we do is we reduce the size, the particle size by grinding. Sometimes you're working with really moist samples like a bar, nutritious bar. It's sticky, it has sugar, it has fat. It's not easy just simply to grind as such. So what you would do is you try to freeze it and grind it frozen. So we call this grinding. Or sometimes you dry it. Usually we try to dry it using the freeze drying method because it's the least impactful on the material. And then you need to determine the moisture content so that you can prepare your samples and measure on dry basis and then convert to wet basis if you know the moisture. But oftentimes you can just freeze it, grind it frozen, call it fine grinding, and then you make sure that it's at a particular mesh size, and you use rototap sometimes to separate based on the particle size. And each level has a different cell with a different mesh number, so you can make sure that your samples pass through 20 mesh. That means you can say that the particle sizes are 20 mesh or less. Or sometimes you want them even smaller at 40 mesh, and this is mainly for extraction procedures. So if you are extracting for fat content, determine fat, you definitely need smaller particle size, larger surface area. And if you're running experiments to extract fiber or extract proteins, you really want to get as small of the particle size as possible. For moisture content or just protein content, you're not extracting or measuring protein or measuring ash content, for example, 20 mesh is sufficient. So we need to eliminate enzyme activity. Why and how? Can you think of why do I want to eliminate enzyme activity? And then how? Why don't I want my sample to have enzyme activity while it is stored until I'm able to analyze? Stella.
We don't want enzyme activity because they can change the values of the body. When you take the sample, you want it to stay the same throughout the sampling process.
Yes, enzyme can hydrolyze proteins, can sometimes you have endogenous enzyme break down starch, break down, sometimes causing lipid oxidation if you have lipoxygenase. So you don't want these enzymes to work and change the composition, especially if you're looking at components that can be degraded by enzymes. So we don't want that. How can I eliminate enzyme activity? How can I prevent enzyme activity in my samples? Yes, Ruth. Huh? You could do heat treatment to inactivate enzyme, but sometimes you don't want to heat because it might impact other components in your sample. You might want to avoid heat. What do you do?
I can cryo-freeze them. Just stop.
Freeze them, yes, temperature. So we can freeze them, we can dry them to reduce the moisture content and therefore reduce water activity. So that's, these are a couple of options to eliminate enzymes. Okay, if I'm looking at fat composition or fat lipid oxidation, or I'm looking at anything related to lipid quality, I want to avoid oxidation during storage so that I don't change my results. So how can I avoid lipid oxidation during storage? When I'm preparing the sample and when I'm storing it until I do the analysis, what can I do to avoid lipid oxidation? From your food chemistry, how can you avoid lipid oxidation? Ian? Away from light. Very good. What else? You're thinking good. Light. What else affects lipid oxidation? Oxygen. So steal it. Flush with nitrogen. You don't want that oxygen. You flush with nitrogen. That means you replace the headspace. Instead of oxygen, you put nitrogen, and oxygen is kicked out, and then you seal. So now we sealed it, and then we put it in without light, We can also freeze it. You slow down reactions in general. You can also add antioxidants during preparation and during storage so that you prevent lipid oxidation. We also want to limit microbial growth because microbes feed on the constituents of the food, so they will change the composition. You don't want that to happen. They might also cause, for safety reasons, you don't want that to happen, especially if you're doing microbiological type of testing. So how do I prevent microbial growth? You have similar things that what you do for any chemical reactions. You want to store it at low temperatures. It's well sealed. You can also put antimicrobial agents or preservatives in there. So anything to prevent growth of microbes, you want to make sure that you do while you're storing or while you're preparing your sample. So the message is avoid sample alteration altogether. So you don't want to change the sample during sample preparation and during storage. So for next, I would say next Monday, if you wish, this is a +5 extra credit. You don't have to do it, just get extra credit if you do it. It's good to practice. This is study question number 7 in your textbook, chapter 5. So try to solve it and bring it to class. Next Monday, I won't be here. Nigel or any of the TAs will take it from you. Nigel, Brittany, whoever is here, just make sure to remind them to hand it. Again, it's not required. You won't lose points, but you will gain points if you do it. Okay. Let's start new topic. So you will notice or you will encounter a lot of reagents throughout the semester in labs. We utilize reagents, sometimes we utilize buffers. So it's very important to know how we prepare these reagents. Any experiment has reagents involved in it. So it's good to refresh your memory on how to calculate molarity, normality, percentage, parts per million. How do we prepare buffers? Buffers are important in reactions. We're going to talk about, we'll have a chapter on pH and buffers later on the semester. When we're doing enzymatic reactions type of assay, we need to utilize buffers. When we're extracting, we might need to utilize buffers. So it's really important to learn what buffers do and how we prepare buffers and how different reagents are prepared. So this topic is going to walk you through a lot of calculations. So some of you remember this from your previous general chem, from high school chemistry. It's just a refreshing. So you might find it very easy. Some of you might find it, I really don't like chemistry and calculations, but it's a good refresh. So a buffer. What do we know about a buffer? A buffer consists of a mixture of weak acids and their conjugate base, has a neutral pH, and stabilizes a certain pH. Yeah.
I think there's A and C.
A and C, great. Any other answers then, Kevin? Anybody want to contradict Kevin? No, it's just like, don't you dare. No. No, it's correct. So a buffer doesn't mean a neutral pH, doesn't have to be a buffer at pH 7. You have acidic buffers, you have base buffers. So, but the buffer in general, the use of the buffer is to make sure that your pH doesn't change over a period of time or during a chemical reaction. So let's say it's an enzymatic reaction that you are carrying out and it has to be at pH 6. So you utilize a buffer at pH 6 to make sure that No matter what happened in the chemical reaction, the buffer is always, or the system is always at pH 6. So it stabilizes a certain pH, and yes, it consists of the weak acid and the conjugate base, so that if you are titrating, let's say if you're adding acid, or the reaction is generating acid or a proton, there is a conjugate base that will capture the protons and prevent the drop in pH. The other way around, if your reaction is releasing OH minuses, so it's releasing alkalinity, then the weak acid is going to capture or provide a proton to neutralize the OH minus. So it will give a proton, and the OH minus is going to react and give you water, and the pH stays the same. So basically, the weak acid and the weak base, or the conjugate base, is neutralizing the environment. Neutralizing the environment, but keeping a specific pH. It's not necessarily keeping the pH neutral. I don't want you to mix that. Neutralizing any change in the environment. It's kind of like, okay, there's an extra protons, you don't want them, you have OH minuses, or you take them, and then the pH doesn't change. Okay, so I don't want to mix you up by saying neutralizing the environment, but maintaining the particularly desired pH. So A and C, just to be clear. All right, so let's remember a little bit of the concentrations or the units of concentrations we have learned back in the days in general chem and also in high school. Molarity equal number of moles per liter of solution. So something you want to remember, molarity as a unit of M, and it is number of moles per 1 liter. Molarity is number of moles per 1 liter. Number of moles equals mass or weight in grams over molecular weight in grams. Normality is number of mole equivalent of the solute per liter of solution. So what does that mean? Let's say H2SO4 is an acid. It has 2 protons. Okay? 1 molarity equals 2 normality. Why? Because normality equals number of equivalents times molarity. So how many H's I have? I have 2. So normality equals 2 times whatever the molarity is. So if the molarity is 1 molar, the normality will be 2 molar. If I have HCl, I have 1 proton. 1 molar equals 1 normal. So this brings me to molecular weight and equivalent weight. Equivalent weight will be important to us when we determine titratable acidity. We have organic acids, and each acid have different number of carboxyl groups. So you have citric acid and 3 carboxyl groups. So you would have 3 number of equivalents. So the molecular weight will be divided by 3 to give equivalent weight. So that's important for calculating percent titratable acidity later on. But in this example, I have 2 number of equivalents. So the equivalent weight is the molecular weight divided by 2, because I have 2 protons. So just to remember, we'll be using this later on in the semester. Percentage concentration, which is the ratio of weight to volume, or volume to volume, or weight to weight, in 100. So grams per 100 grams, milliliter per 100 milliliter, or grams per 100 milliliter. So percent, we always indicate like weight by volume, I will tell you, or volume by volume, or weight by weight. So whenever I give you a percentage, I would declare whether it's weight by volume by volume, or weight by volume. And then when the concentrations are really low, really under 1%, very small concentration, we can report them as parts per million. ppm. So we will be using this term when we measure. Are we going to do caffeine parts per million or no? It's going to be parts per million. So it will come to you later on in some of the labs. Parts per million, meaning milligrams per kilograms or milligrams per liter, or micrograms per milliliter, that's also parts per million. And there's parts per billion, which is microgram per kilogram or microgram per liter, and then parts per trillion as well. So nanograms per kilogram or nanograms per liter. So that some analyses usually can have very low threshold or detection limit. So we can detect with very, very small concentration. Parts per billion, parts per trillion, and it can go lower as well. One thing I want to remind you of, which we will be using a lot, is the equation of equilibrium or neutralization. When we're talking acid-base, we call it equation of neutralization, but also it is equation at equilibrium. So milli-equivalent of one reactant equals milli-equivalent of another reactant. You probably remember that. And usually it's either liter or milliliter. If we say milli-equivalent, then it's milliliter. If we say equivalence of, then it will be volume in liters. So milliliter of a certain solution times the normality equals milliliter of another solution times 1 And we're going to use it a lot when we're doing dilution protocols, when we are diluting to prepare a certain concentration of a particular reagent. So when we buy HCl from the market, it's usually a concentrated HCl container. And then we need to prepare a specific concentration for our experiment. So in this case, we buy a solution of HCl, a bottle that has a normality of 12 norm. And I ask you to prepare 1 liter of 0.1 normal HCl. Pull out a piece of paper and let's start calculating. Write your name on the piece of paper. And keep it with you for next lecture on Wednesday. We're going to continue with calculations. But let's practice preparing 1 liter of 0.1 normal HCl from 12 normal stock solution. So basically, I want you to tell me how many milliliters of my stock solution I need to take out and dilute to 1 liter so that I can get the solution of 0.1 normal HCl. Anybody with an answer? No?
Yeah.
What do you have?
On 1/20th of the year.
128? Can you give me,
One.
can you give this to me in milliliters? 8, 8, 8, 8.33 milliliters. Okay, I will write down how we got to that. Oh. All right, we said we're gonna use the equilibrium equation. And I'm gonna say X milliliter times normality. I want to prepare 1,000 milliliters of 0.1 normal. So I have the normality of my stock solution, which is 12 normal. And I want to say how many milliliters I need of my 12 normal so that I can prepare 1,000 milliliter of 0.1 normal. So I will just solve for X milliliters, would be 1,000 milliliters times 0.1 normal divided by 12 normal. So 100 over 12, the normal, this unit and this unit cancel, the normal cancels, and then the answer will be in milliliters, and that's 8.33 milliliters. If you write in exam 8.33 milliliters and stop there, I will deduct a little bit of points. Why? What's that?
The units.
The units are correct.
Well,
Yes, Isaac?
milliliters of what it is.
Yes, well, what it is in what? So I would say I would take 8.33 milliliter of 12 normal HCl in 1 liter volumetric flask. You're gonna tell me how I'm gonna prepare it, right? And make up to volume with water. So you wanna finish the job. And usually distilled water or double distilled water. And also, for good measure, I'm not gonna take out points on that. So you would have your flask, you would say, I would put a little bit of water in the flask because you don't want to pour acid on water. I'm sorry, water on acid. If you put 8.33 milliliter and then you put water on top, it will splash on you. So you want to put a little bit of water, put the acid in, and then dilute up to the mark with water. That's the technique that you would use in a lab. But in an exam, you want to say 8.33 milliliters of the concentrated stock. I will put it in a volumetric flask that is 1 liter and make up the volume with water. That's your complete answer of how to prepare a 0.1 normal HCl. Stop here, and I'll see you on Wednesday.